Okay, this is lecture 4. We start discussing chapter 2, which talks about the addressing modes. We previously mentioned that each and every memory location, each and every I/O port should have a unique address, and there are different addressing modes in dealing with memory and I/O ports from the point of view of microprocessors. Okay, so we're going to discuss the addressing modes, the stack. What do we mean by the stack? And we have two types of addressing modes. One mode regarding the data and another mode regarding the program memory locations. Okay. The data addressing mode. We start with the data addressing mode. In order to comprehend the data addressing mode, we will have to use some good and useful assembly instruction, which is move. So let's see what does this instruction do. The move instruction is written as MOV, which takes two operands and separated by a comma. We place the source from which we get the data to the right of the comma and the destination, the place where we store data in. We take the data from the source to the destination. So the source location is written to the right of the comma, and the destination location is written to the left of the comma. And the data moves from source to destination. What this move instruction does is this. It's just copying the data from the source to the destination. So the data that was in the destination will definitely change, while the data in the source will be kept intact. So if you need the old data that was there in the destination, you'd better place it somewhere else. Okay, how to describe the source location and the destination location? This is the purpose of the addressing mode. We have different addressing modes to describe both source and destination location. Okay, data addressing modes are register addressing mode. This is one of the modes, or immediate addressing modes, direct addressing, register indirect, base plus index addressing, register relative addressing, and finally the base relative plus index addressing mode. So we'll talk about each one of these 7 different modes at a time. So let's start on port addressing. Okay, this is regarding memory locations 7, and this is regarding the I/O port. Okay, so let's talk about the first mode of them, which is the register addressing mode. This mode is used to transfer data. Data is a byte or a word from a source, which is a register, to a destination, which a register. This is why it's named register addressing mode. It takes the data from a register, byte or word, as a source, and places it in a register, byte or word, as a destination. And we have 8-bit registers, 8-bit registers named as such, and the 16-bit registers inside your 8086, 8088 processors are listed here. And there are some rules you have to abide by, you have to comply with in dealing with register addressing mode. The first rule is that your source, the place you take the data from, and destination, the place you place data in, should be of the same size. So you take an 8-bit from the source, you place it in an 8-bit in the destination, If you take 16 bits, you have to prepare a destination location of 16-bit wide. And it's not allowed to move from one segment register to another. So you don't make your source and destination segment registers. This is not allowed. So these are two rules you have to comply with in dealing with the register addressing mode. Alright, this is now the first addressing mode, which the register addressing mode. Here are some valid and invalid instructions. Here, for example, you placing an 8-bit register, the content of 8-bit register into another 8-bit register, no problem. The value from BL is placed now in AL. If you look at these three instructions, they are invalid. Here you're trying to move the data from a segment register to another segment register, which is not allowed. Here you are trying to place 16-bit register into an 8-bit register. You cannot do this. Here you're trying to place 8-bit register, the value inside 8-bit register into a 16-bit register. This is again not allowed because you have to specify which register you'd like to place DL in. Is it AL or AH? You can never leave it as such 8-bit and 16-bit registers. Okay. This example of register addressing mode, move BX comma CX, this will take the value from the 16-bit register CX, place it into the 16-bit register BX. For example, if this is the value inside BX before execution, and this is the value inside CX before execution, what this instruction does, it takes this value from CX, place it into BX. So the value inside BX is going to change while the value inside CX will be the same. Okay, after execution, here the value inside BX becomes as the value inside CX. So CX kept its previous value while BX changed the value inside to be 123H hexadecimal. Okay. The second mode is the immediate addressing mode. Immediate means a value. Okay, you place a value inside an address immediately. So it takes to transfer, it is used to transfer immediate byte or word, immediate value inside a destination register. Okay, the data is placed immediately in the instruction. Here is an example. So here you're trying to place an immediate value 44 inside VL. If you do not write H after 44, it means this 44 is a decimal number whose hexadecimal equivalent is 2C. So what this instruction does, it takes a 2C as a hexadecimal value, place it into BL. Here, this 44 is a hexadecimal number, so you are allowed to place immediate 8 bits into a 16-bit register because this 8 bits will be placed in your AL while your AH will become 0. Alright? 0 inside SI. Okay, whether it's hexadecimal or decimal, 0 is 0. Takes 4 zeros, place them into SI. This 100 is to be dealt as a decimal number whose equivalent hexadecimal is 64. So it takes 64, place it into CH, and so on. Okay, example, move AX comma 3, 4, 5, 6 hexadecimal. So this will place 3, 4, 5x into AX. So before execution, the value inside AX is given. This is definitely going to change, and this 6291 will be lost. After destination, this value becomes 3456 hexadecimal. Okay, then the third is the direct addressing mode. What this mode does is to transfer byte or a word from a memory and a register or vice versa between memory and register. Okay, the memory address is given by its effective address or offset. So how many memory locations you need to move up from the value inside the segment register. This is what's known as effective or offset address. Okay, for example, the physical address is given by the value inside a segment register times 10, and you add the number of locations you need to move up to get the required memory location. This is done by adding an offset or effective address. They are used interchangeably, offset or effective address. Okay, and this can be written as this effective address can be given as a label. You label some memory location inside your memory segment and you go to this name, or you move up, you make some displacement, you move some memory locations to reach to this required memory location. So you can name or label a memory location, or you determine how many steps you need to get displaced to get to the correct memory location. So direct address by label, this is you refer to the memory location by label beta. Okay, so your processor will go to this memory location labeled by beta and try to get data to place them into AX. But it needs two memory locations because you're trying to fill up a 16-bit register. So it goes to beta, place the 8 bits in beta inside your AL, and goes to beta plus 1, the high, inside your AH, low and low, high and high. This is the little Indian format we talked about previously. All right. So you go first to your data memory segment, multiply the value by 10, add beta. So this is the first 8 bits to be placed in your AL. Then you go to beta plus 1, the second 8 bits to be placed inside your AH. Okay, example. All right, here you have a label number. So you go to number and get 8 bits, place them in AL. You don't have to go to number plus 1 because you're trying to fill up an 8-bit register. Where here you have 16 bits inside AX. So you go to there, place your low byte, go to there plus 1, place your high byte. So you need to go to there and there plus 1. Okay, again, this is the memory location labeled number 1. You go to number 1, get 8 bits. So number 1 is 1, 2, 3, 4, and the S is equal to this. So your physical memory location number 1 is now ds times 10 plus 1, 2, 3, 4, 5. So this is your physical memory location. You go there and get 8 bits, place them into AL. Okay, and this is true only with AX, AL, and AH. Okay, before execution, this is your AH, AL. Regardless of the value inside, you will go to the memory location defined by this physical address. You will find 12. All right, so this 12 now is to be placed inside your AL while AX is filled with 0 or left as is. Left as is. Okay, you place 12 inside your AL and you leave your AH as is. It's not filled with zeros unless you give an immediate value. If the value is given by a label, you determine 8 bits inside AL. So you take the 8 bits, which is 12, place them inside AL, leaving AH as is. Okay. So if it's not given by a label, it's given by a displacement. All right. So this is the displacement. Okay. When you place an immediate number inside these two square brackets, it means this is not an immediate number, it is an address. So this is the effective address. So you're trying to get 16 bits from memory whose effective address is 1, 2, 3, 4. Place them into CX. So you would have to go to the physical address first. Data segment times 10 plus 1, 2, 3, 4. You get the low byte. Data segment times 10. 1, 2, 3, 4 plus 1. You get the high byte, CH and CL. For example, here you go to DS times 10 plus this number, DS times 10 plus this number. You need only 8 bits. You get 8 bits, you place them in CL. Okay, so you don't have to go to this number plus 1. While here we're trying to place 16 bits into memory. This value, the address of the there inside memory, is given by ds times 10 plus there, but you have to go to ds times 10 plus there plus 1. You need to get a low byte from here and a high byte from here. You place them into your bx. Okay, we're still discussing the displacement address. This is an example. Before execution, this is your ds. Physical address is ds times 10 plus this. So this is now the address of your low byte. Okay, so this is your cx, regardless of the values inside your cx, cl, and ch. You need to go to memory and you have to define two memory locations. Lower address to go to cl, higher address to go to ch. So the value goes to this value goes to ch, while this value goes to cl. Okay. Okay, another register mode is the register indirect. What this mode does, it takes a byte or a word between a register and memory location. But now this memory location has an address, and the address is given inside another register. So you don't go to the memory location by a label or directly. You go to this memory location by an address stored in a register. Okay, and the registers used to point to a memory locations are BX, BP, SI, and DI. So these registers store the address of a memory location. For example, move AX SI. Again, SI is placed between two square brackets, meaning the value inside SI gives you the offset or the effective address of a memory location. All right, and here we're trying to place 16 or to get 16 bits from memory to fill out AX with. So you have to go to SI and SI plus 1. You go to SI and SI plus 1 to get the low byte to be placed in your AH, to be placed in AL, and the high byte to be placed in AH. Okay, here are some instructions. All right, now BX refers to some memory location. DS times 10 plus BX, you get the low byte of CH, you place this in CL, then you go to DS times 10 plus BX plus 1. This is to be placed in your CH. This is the higher address to be placed in CH, and this is the lower address memory location to be placed in CL, again following the little endian format. Here, BP takes a value from your stack, not the data memory segment, of the stack memory segment, and you need only to get 8 bits from the stack because you're trying to fill out the DL, which is composed of 8 bits. So you go to SS times 10 plus BP, SS times 10 plus BP. This refers to a memory location in your stack memory segment. You get 8 bits from there and place them into your DL. Here, again, what's the value inside DL refers to an address, square bracket. So you need to fill 8 bits coming out of BH inside this memory location. DI usually goes with ES. So you get ES times 10 plus DL. This is the memory location to where the 8 bits from BH is to be placed. Register indirect. Okay, this is an example. Before execution, you're given the value of SI. Okay, and DS times 10 plus SI. This is a value and a physical address inside your memory. So this is the value stored in an address referred to by SI. Okay, and you have to go to SI plus 1. So this is to be placed lower address in AL, and this is from the higher address is to be placed in AH. Okay, so after executing this, this is your AL and this is your AH. And the value inside your SI does not change. Another example, here you go to the stack. All right, get 2 memory locations from the stack, 16 bits to be placed inside your CX. Here is the stack, okay, lower address, higher address, lower address in CL, higher address in CH. Here is, after execution, here is your CL and CH. Okay, here is another addressing mode which is called base plus index addressing mode. So you have to go to somewhere inside your memory pointed to by base, and from there you have another index register to move you upward or downward. So this is used with string instructions and if you have blocks of data or an array of data. So it is used to transfer a byte or a word from some memory location addressed by the base register plus an index register. So this memory location has a starting point and you move up or down by an index register. Again, used with string instructions or when dealing with array. Okay. So the base gets you to the beginning address of an array or the starting address of an array. And whether you go upward or downward, this will be determined by your direction bit, the D bit inside your flag register. Okay, again, the index will get you the relative position from, or the array element inside your array is determined by your index register. For example, here, you're trying to place 8 bits, which is an array element inside some memory location. You're trying to fill up an array whose starting address is bx and the current element is determined by si. So you go to ds times 10 plus bx plus si, you get a memory location into which you store the 8 bits from AL. Okay, ds again times 10 plus bx plus si gets you a memory location to which you place your 8 bits. Here Okay, again, you go to ds times 10 plus bx plus si and plus si plus 1 because you need to get 16 bits lower address memory location in CL, higher address memory location in CH. Here you are. This is the lower address. This is the lower address memory location, and this is the higher address memory location plus 1. Here you go again to the stack memory segment. You go to some address determined by these register and index register SS times 10 plus BP plus DI. Sn times 10 plus BP plus DL gets you a memory location inside your stack memory segment. You get 8 bits from DL and place them into your stack. Okay, this is another addressing mode called register relative addressing mode. Again, it is used to transfer a word or a byte between register and memory location. The memory location is now determined or indicated by the sum of the content of a register and a direct or indirect displacement. Okay, we'll see this by an example. Again, the registers used to store addresses in are these 4 registers. For example, here you are trying to get 8 bits from AL, place them into somewhere inside your memory. This somewhere is determined by an address and a label. So this is your memory. Okay, the starting or the beginning of this that memory segment is ds. You move to some displacement determined by bx, then from there on you have a label called beta, and you go to this memory location, store your ALN. Okay, so your location now is ds times 10 plus bx plus beta. All right. Here are examples of these register relative addressing modes. Okay, here is an example of the relative register relative addressing mode. We're trying to get 8 bits from the register AL, place them into some memory location inside your data memory segment, referred to by bx and beta, a value inside the register and a label. So you take the S, okay, this is the value inside your bx. You will have to go to this memory location by multiplying ds by 10 plus bx plus beta. Okay, so the s times 10 plus bx plus beta gives you this address whose content in this. It gives you the higher address location and the content in this. We need only the lower address memory location. Okay, whose content in ED. Now you take AL, which is ED, and place it into this address. It happens that the data to be replaced with is the same. So AX will get, okay, EDBE, and the memory location will get 87ED, 87ED. Okay, because this memory location AL is rewritten inside your lower address memory location. The higher address is kept as is. So ED, so it's sort of rewriting AD over AD. Okay, another addressing mode is base relative plus index. So you're trying to transfer word or a byte between a register and memory location. This memory location will be addressed by base register plus an index register plus a displacement. This is used when you have your memory segment as a folder, and inside this folder you have many arrays or many files. Okay, the first file is pointed to by the base register, and you go to each line inside this file, or you have different arrays. Okay, you go to the starting element of the array and use your index register to go over the elements, the different elements inside your array. The base address that gives you the starting element of another array, and you go by SI to access the second array. All right, for example, here you have a value of 8 bits inside AL. You need to place it specifically in an array element whose starting address is BX, and you go to inside this BX, you go to somewhere by SI, specifically inside this array, you have a memory location labeled by beta. Go there and replace the 8 bits inside this. All right, dx times 10 plus bx plus si plus beta. Okay, here are examples. You can follow them easily. Okay, here is a numerical example of this addressing mode. So we're trying to get from the stack memory segment, okay, two memory locations, two elements in an array. This array is inside some file whose starting address is BP, and this is the starting of the array element, and this is the specific element we need to access from this array. So you go to SS times 10 plus DI plus beta and plus beta plus 1. All right, so before execution, this is your BP, okay, and this is your DI. Okay, memory SS times 10 plus BB plus DI plus beta. It gives you this address. You go to this address and to the higher one. So this low address data is to be placed in CL, and this is the high addressed data is to be placed in CH. So after execution, you should find ABEC inside your CX. ABFC. ABFC. Okay, good. And here the summary of the different addressing mode explained schematically, which summarizes the different addressing modes. And this is the end of lecture 4. See you in lecture 5.